Tonight, we're diving into a concept that sounds simple, yet is one of the most mind-bending ideas in all of science: the light year. You've heard this term countless times. Astronomers use it every day when talking about space. But here's the surprising truth: very few people actually understand what a light year means. And once you finally grasp the distance it represents, it changes the way you see the universe. It isn't just a big number. It's a distance so vast that it pushes the limits of human imagination. By the end of this journey, you'll understand why astronomers rely on this measurement, and why no other unit would make sense. Before we begin, if you enjoy deep, calm explorations like this, a quick like or subscribe really helps the channel grow. Now, let's get started. Let's begin with something familiar: distance. In everyday life, distance is simple. You know how far the grocery store is. You know the route to work, or the drive to the next city. These are distances you can picture because you've experienced them. A kilometer? That's just a 10 to 12-minute walk. These measurements work perfectly for daily life. If someone says a store is 5 kilometers away, you instantly understand the trip: a short drive, a few turns, maybe a couple of traffic lights. It's concrete and relatable. If a city is 200 kilometers away, you plan a 2-hour drive, grab some snacks, maybe stop halfway. These distances make sense to us because they fit into our human experience. We evolved to understand the distance we can walk in a day, what we can see with our eyes, what matters for survival and navigation. But these same measurements start to feel awkward when we deal with much larger scales. The distance from New York to Los Angeles is about 4,500 kilometers. Still manageable. It's a 5-hour flight. People do it all the time. You can imagine crossing the continent, cities, plains, mountains, deserts, and finally the Pacific coast. A long journey, but still within human capability. The Earth's circumference at the equator is about 40,075 kilometers. A huge number, but still something we can wrap our minds around. Explorers have sailed around the planet. Airlines can fly around it in less than 2 days. The Earth is large, but not beyond comprehension. In theory, you could explore the whole thing. But now let's push farther. The distance from Earth to the Moon is about 384,000 kilometers. And suddenly, kilometers start to lose their usefulness. 384,000 kilometers is not a road trip. It's not like sailing around the world. It's something entirely different: pure distance across empty space. No scenery, no landmarks, no stopping points. Just a vast stretch of nothing. How would you even travel that far? The Apollo astronauts took about 3 days to make the trip, riding rockets that pushed them to speeds of about 11 kilometers per second, nearly 40,000 kilometers per hour. That's around 400 times faster than highway driving. Think about that. 400 times faster than anything you've ever sat inside. And even at that unbelievable speed, powered by some of the most powerful rockets ever built, it still took 3 full days to reach our closest celestial neighbor. And the Moon is close. You can see it with your naked eye. You can see its craters with binoculars. It hangs right there in the night sky, yet it takes days of high-speed travel to reach it. Now imagine trying to measure the distance of planets to the Sun or to other stars. Kilometers become meaningless. The numbers explode into values so large that they lose all connection to reality. They become abstract, symbols on paper rather than distances you can feel. Take the distance from Earth to the Sun, about 150 million kilometers. Try to picture that. You can't. Your brain sees it as a huge number, but nothing in your daily life prepares you for that kind of scale. Humanity didn't evolve to comprehend 150 million kilometers. We evolved to understand a walk to the next water source. If the Apollo spacecraft, traveling at 11 kilometers per second, headed toward the Sun, it would take about 160 days, more than 5 months, just to reach its distance. The fastest spacecraft ever built, the Parker Solar Probe, speeds up to 192 kilometers per second when it slingshots around the Sun. Even at that incredible speed, 17 times faster than Apollo, it still takes months to complete a single orbit. And remember, the Sun is close. It's our local star. We see it every day. It warms our planet. It makes life possible. Yet it's unimaginably far away. When we begin talking about distances to other stars, even the Sun's distance becomes tiny. That's when we need a measurement bigger than kilometers. A measurement built for the scale of the universe. And that's where the light year enters the story. It's familiar, and yet it's 150 million kilometers away. A distance so vast that even our fastest spacecraft take months to travel it. And when we begin talking about the distances to other stars, even the sun's distance becomes tiny by comparison. The sun is our nearest star, and it's 150 million kilometers away. But the next nearest star, Proxima Centauri, is about 266,000 times farther than that. 266,000 times farther than a distance that already takes months for our fastest spacecraft to cover. This is why astronomers needed a different unit of measurement. Not to make things complicated, not to confuse people with huge numbers, but because kilometers simply don't work when measuring cosmic distances. Using kilometers to measure distances to stars is like using millimeters to measure the distance between countries. Technically possible, but completely impractical. The numbers get so large they lose all meaning. They stop being distances and become abstract numbers that don't connect to anything we experience. So astronomers came up with something different, the light year. And here's what you need to understand right away. A light year is not a measure of time. Even though it has the word year in it, a light year measures distance. It is the distance that light travels in 1 year. And why base a measurement on light? Because light is special. Light is the fastest thing in the universe. Nothing can travel faster than it. Not because we haven't built something fast enough, but because the laws of physics forbid it. The speed of light is a constant, unchanging, universal, and the same everywhere you go. Light travels at about 300,000 kilometers every second. The exact number is 299,792.458 kilometers per second, but 300,000 is close enough for us. To put that speed in perspective, light can circle Earth about 7.5 times in 1 second. In the time it takes you to snap your fingers, light can travel around the entire planet multiple times. In 1 second, light could travel from New York to Los Angeles and back roughly 37 times. Nothing in our everyday life moves anywhere near the speed. A commercial airplane flies at about 900 kilometers per hour, around 0.25 kilometers per second. Light is over 1 million times faster. The fastest car ever built, the Thrust SSC, reached 1,200 kilometers per hour, or 0.33 kilometers per second. Light is about 900,000 times faster. Even the fastest spacecraft humans have built, the Parker Solar Probe at 192 kilometers per second, achieves only about 0.064% of light speed. By human standards, it's unbelievably fast, but compared to light, it's crawling. When you turn on a light switch, the light reaches your eyes almost instantly because the distance is so small. The light travels from a bulb to your eyes in about 10 billionths of a second, so fast that your brain can't detect a delay. But the light still takes time to travel. It's just so little that you don't notice it. When you see the sun in the sky, you're seeing it as it was 8 minutes and 20 seconds ago, the time it takes sunlight to travel from the sun to Earth. If something happened on the sun right now, we wouldn't know for over 8 minutes. The light carrying that information hasn't arrived yet. When you look at the moon, you see it as it was 1.3 seconds ago. During the Apollo missions, every message from astronauts on the moon took 1.3 seconds to reach Earth, and responses took another 1.3 seconds to return. That's why communication recordings have a noticeable pause. Even radio waves, which travel at the speed of light, need time to cross the distance. Before the 1600s, most people believed light traveled instantly. But in 1676, Danish astronomer Ole Rømer studied the moons of Jupiter and discovered that the timing of their eclipses changed depending on Earth's distance from Jupiter. When Earth was farther, the event appeared delayed. He realized light takes time to travel. Although his calculations weren't perfect, because the size of Earth's orbit wasn't precisely known, he proved light has a finite speed. Today we've measured the speed of light with incredible precision. And we've discovered that light speed is woven into the structure of the universe itself. It's not just how fast light moves. It's a fundamental property of space-time. A light year is the distance light travels in 1 year at this constant speed. 300,000 kilometers per second multiplied by 60 seconds, 60 minutes, 24 hours, and 365 days. The result is about 9.46 trillion kilometers. That's what a light year is, 9.46 trillion kilometers of distance. But to understand how huge this distance really is, we need to understand what a trillion is. A million is 1,000,000. A billion is 1,000 million. But a trillion is 1,000 billion. If you saved $1 per second without ever stopping, it would take over 31,700 years to reach $1 trillion. That's longer than all of recorded human history. Agriculture began about 10,000 years ago, writing about 5,000 years ago, the pyramids 4,600 years ago. To count to $1 trillion, you would have had to start long before any civilization existed. And a light year is 9.46 trillion kilometers. That means it's like walking 9.46 trillion individual kilometer-long steps, each one the length of a 10 to 12-minute walk. The scale is unimaginable. Let's build up to it step by step. 1 light second is 300,000 kilometers, about the distance from Earth to the Moon, and most of the way back. 1 light minute is 18 million kilometers. The Sun is 8 light minutes from Earth. NASA's rovers on Mars operate with a time delay because signals take anywhere from 2 to 22 minutes to cross the changing distance between Earth and Mars. 1 light hour is over 1 billion kilometers. When the Cassini spacecraft was orbiting Saturn, each photo it sent took more than an hour to reach Earth. Engineers couldn't control it in real time. They had to pre-program long sequences of instructions. 1 light day is 25.9 billion kilometers. Voyager 1, the farthest human-made object, launched in 1977 and traveling for almost 50 years, is still only about 1 light day away. That's how huge cosmic distances are. 1 light week is 181 billion kilometers. 1 light month is 778 billion kilometers. At that distance, the Sun begins to look like an ordinary star. The entire solar system shrinks to a tiny speck. And finally, 1 light year, 9.46 trillion kilometers. This is a unit astronomers use to measure the distances between stars because nothing smaller makes sense. Why use light years instead of kilometers? Because saying Proxima Centauri is 4.24 light years away is far more meaningful than saying it is 40 trillion kilometers away. Light years also connect distance and time. A star 4 light years away is seen as it was 4 years ago. The farther we look into space, the further back in time we are seeing. The speed of light is not just fast, it is a speed limit of the universe. Einstein's special relativity explains that as objects approach light speed, time slows down for them, distances contract, and mass effectively increases. To reach the speed of light would require infinite energy, which is impossible. Particles and accelerators live longer when moving near light speed due to time dilation. GPS satellites must correct for these relativistic effects, or their positioning data would drift. The speed of light remains constant for all observers, no matter how fast they are moving. It's a fundamental constant shaping the relationship between space, time, matter, and energy, and understanding it, and the enormous distance of a light year is essential to understanding our place in the universe. To begin with, the breakthrough starshot idea requires something almost unimaginably extreme, incredibly powerful lasers. The proposal calls for a laser array with a total power output of about 100 gigawatts, roughly the combined output of 100 nuclear power plants. All of that energy will be focused into a single, precisely controlled laser beam several kilometers wide. That beam would have to keep the spacecraft perfectly centered as it accelerates. If the beam drifts even slightly, the tiny probe would slip out of alignment, the acceleration would stop, and the mission would fail. Next, the spacecraft itself must survive the journey. At 20% of the speed of light, you're traveling at around 60,000 kilometers per second. At this speed, even the smallest particle becomes deadly. A speck of dust, smaller than a grain of sand. Striking the probe at that velocity would explode with the force of a large bomb. The probe needs shielding, but shielding adds weight, and weight is the enemy. The heavier the probe, the more laser power you need to push it. Add more weight, and the entire system becomes exponentially harder. There's also the challenge of communication. The spacecraft must send data back to Earth from 4.24 light years away. At that distance, any signal spreads out so much that even a powerful transmitter becomes whisper quiet. And yet the probe is only the size of a computer chip. Somehow, it would need to carry a communication system capable of shouting across interstellar space and still being heard. Then comes the navigation problem. This tiny gram-weight spacecraft needs to fly past the Proxima Centauri system at exactly the right angle and distance to capture useful images and measurements. At 20% light speed, the probe crosses the orbit of Mars in about 40 minutes. It crosses the entire solar system, from the Sun to Neptune, in roughly 6 hours. There's no slowing down, no turning, no mid-course corrections. Slowing down would require as much energy as speeding up, and that energy simply can't be stored in something so small. So you get one chance, one flyby, a few hours, maybe a few days, near the target star, and then it's gone forever, drifting into the dark between the stars. So while Breakthrough Starshot is grounded in real physics, the technology remains theoretical. We don't have the lasers, the materials, the shielding, or the communication systems. And even if we somehow built everything tomorrow, the earliest we would receive data would be 24 years from launch, 20 years for the journey, plus 4 years for the signal to reach us. And that's assuming everything works perfectly, which in the history of space exploration is rare. This is just to reach our nearest stellar neighbor. With the spacecraft technology we have today, with current rockets, current materials, current computers, reaching Proxima Centauri wouldn't take decades. It would take thousands of years. We would need generational ships, massive vessels carrying human crews who live and die on board while their descendants continue the mission. The people who arrive will be hundreds of generations removed from the ones who launched, traveling to a star they've never seen with their own eyes, guided only by stories and instructions passed down through centuries. And this brings us to something profound. When you look up at the night sky, you're seeing stars not as they are now, but as they were. Because distance and time in the universe are inseparable. Light takes time to travel. It's fast, but not instant. And during that travel time, stars can change. They can dim, flare, or even explode. The star you see shining tonight may already be gone. Take Sirius, the brightest star in our night sky. It's 8.6 light years away. The light you see from Sirius tonight left that star 8.6 years ago. If you're 20, you're seeing Sirius as it was when you were 11. If you're 40, you're seeing it as it was in your early 30s. The Sirius you see isn't the Sirius of today. It's a message from the past. Now consider Vega, about 25 light years away. If you're 25 years old, the light you're seeing tonight began its journey the year you were born. You didn't exist yet when that photon started moving toward Earth. Your parents might have looked at Vega decades earlier and seen even older light. And then there's Betelgeuse, the red supergiant in Orion, about 550 light-years away. The light you see tonight started its journey in the year 1474. Leonardo da Vinci was 22 years old. Michelangelo hadn't been born yet. Columbus had not sailed across the Atlantic. Most of Europe was still transitioning out of the Middle Ages. And through all of this, through centuries of human history, that light traveled through space until it finally reached your eyes tonight. Betelgeuse is massive, unstable, and nearing the end of its life. At some point in the next 100,000 years, it will explode in a spectacular supernova, shining as bright as a full moon. But it might have already exploded centuries ago. If Betelgeuse went supernova in 1700, we won't see it until around the year 2250. The star could be gone right now, and we would have no idea. We would still see its ancient light, the last image of a star that no longer exists. Polaris, the North Star, is about 445 light-years away. When the light we see tonight began traveling toward Earth, the first permanent English colonies in North America didn't exist yet. Jamestown hadn't been founded. Humanity had no telescopes, no electricity, no concept of galaxies, black holes, or the speed of light. And yet the photons from Polaris were already on their way. This is a cosmic truth of light years. Every time you look into the night sky, you're looking into history. You're seeing the universe not as it is, but as it was, distance and time woven together in the fabric of space itself. Jamestown wouldn't be founded for another 12 years. The Pilgrims wouldn't step onto Plymouth Rock for another 26. William Shakespeare had only just begun writing his plays. Some of his early works existed, but he hadn't yet written Hamlet, Macbeth, King Lear, or most of the masterpieces we know him for today. And the United States? That wouldn't exist for nearly 180 more years. So when the light from Polaris began its journey toward Earth, the world was a completely different place. And tonight, that ancient light reaches your eyes. You are connected across space and across centuries by photons that have been traveling for 4,500 years. Within about 20 light years of Earth, astronomers have identified around 130 star systems. Some contain a single star like our Sun. Others are binary systems where two stars orbit each other, or even triple systems like Alpha Centauri. Understanding this local neighborhood helps us appreciate not only the enormous distances involved, but also the diversity of stars surrounding us in our corner of the galaxy. Barnard star is the second closest stellar system after Alpha Centauri, roughly 6 light-years away. It's a red dwarf, smaller, dimmer, and much cooler than the Sun. What makes Barnard star remarkable is its speed. It has the greatest proper motion of any known star, meaning it visibly shifts across the sky over decades and centuries. Eventually, in about 10,000 years, Barnard star will move closer to Earth than Proxima Centauri is now, becoming our nearest neighbor. But even then, it will still be almost 4 light-years away. That's how vast the gaps between stars truly are. Even when stars are moving toward each other at impressive speeds, it takes tens of thousands of years for any real change in their distance. Wolf 359, about 7.9 light-years away, is another fascinating example. It moves at roughly 119 kilometers per second, extremely fast by stellar standards, considering most nearby stars drift at only a few tens of kilometers per second. Yet even at that speed, Wolf 359 is traveling at just 0.04% of the speed of light. Stars move, but compared to the distances separating them, their motion is incredibly slow. Even the fastest nearby star would need tens of thousands of years to travel a single light-year. Sirius, 8.6 light-years away, is not actually a single star but a binary system. Sirius A is a bright, white main sequence star about twice the Sun's mass. It's the brightest star in our night sky, partly because it's close to us and partly because it's naturally very luminous. But its companion, Sirius B, is entirely different. A white dwarf, the dense core of a star that has already burned through its nuclear fuel. White dwarfs are extraordinary. They pack the mass of a star into a sphere roughly the size of Earth. Sirius B contains nearly the same mass as our Sun, compressed down into an object only slightly larger than our planet. The density is unimaginable. A teaspoon of Sirius B's material would weigh about 5 tons on Earth. The two stars orbit each other every 50 years, bound together by gravity, circling a shared center mass. Now let's zoom out. The Milky Way is a spiral galaxy containing somewhere between 100 billion and 400 billion stars. That number is uncertain because counting stars from inside the galaxy is like trying to count trees while standing deep inside a forest. Dust clouds block our view. Faint stars are easy to miss, and the galaxy is simply enormous. But most estimates suggest around 200 to 300 billion stars, and our Sun is just one of them. An ordinary, average, unremarkable yellow star among hundreds of billions. Our Sun sits inside one of the spiral arms, about 26,000 light-years from the galaxy's center. Meaning, if we could somehow see directly through the thick dust clouds, the light reaching us from the galactic core will be 26,000 years old. When that light began its trip, humans were still hunter-gatherers in the Stone Age. There were no farms, no cities, no writing, no civilization. We lived in small bands, tracking animals and gathering plants. Writing wouldn't be invented for another 21,000 years. Everything that we think of as human history has unfolded while that light crossed space to reach our world tonight. And the Milky Way itself is huge, roughly 100,000 light-years across. Even traveling at light speed, a journey from one end to the other would take 100,000 years. Modern humans have existed for about 300,000 years. So if someone had started crossing the galaxy at light speed when our species first appeared, they would still be only a third of the way across today. The Sun orbits the Milky Way center at about 230 kilometers per second. That's fast. Fast enough to cross the United States in under 3 minutes, or circle the Earth in about the same time. But even at that speed, the Sun needs roughly 225 to 250 million years to complete a single orbit around the galaxy. The last time the Sun was in its current position, dinosaurs had just begun to evolve on Earth. Since then, dinosaurs rising, dominating for millions of years, vanishing, mammals expanding, humans emerging, the Sun has made only one full revolution. And we're only now returning to the same part of the galaxy where dinosaurs first appeared. One of the most remarkable discoveries in modern astronomy is the detection of exoplanets, planets orbiting stars beyond our sun. Before 1992, we knew of only one planetary system, our own. Then, in 1992, astronomers discovered planets orbiting a pulsar. In 1995, they detected the first exoplanet circling a sun-like star. Since then, the discoveries have exploded. By 2024, more than 5,000 exoplanets have been confirmed, with thousands more awaiting verification. Among the most intriguing is the TRAPPIST-1 system, about 40 light-years away. It hosts 7 Earth-sized planets orbiting a tiny red dwarf star. 3 of them lie within the habitable zone, where liquid water could exist. When this discovery was announced in 2017, it shifted our understanding of a universe. It proved that small, cool red dwarf stars, which make up about 70% of all stars in the Milky Way, can host multiple rocky planets, meaning Earth-like planets might be far more common than we once believed. The TRAPPIST-1 planets orbit astonishingly close to their star, or 7 closer than Mercury is to our Sun. Yet because TRAPPIST-1 is so small and cool, 3 of the planets receive roughly the same amount of energy that Earth receives from the surface of one planet. The others would appear enormous in the sky, some larger than our moon looks from Earth. In theory, travel between them might be more practical than travel between the planets of our own solar system. But when we observe TRAPPIST-1, we're seeing it as it was 40 years ago, back in 1985. If intelligent life existed there and began broadcasting radio signals in that year, we'd be receiving them now. And if we replied, our message would reach them in 2065, an 80-year round trip for a single conversation. You could ask a question and die long before receiving the answer. This is a strange reality of distance in a universe measured in light years. Communication becomes painfully slow. Settlements across light years couldn't have conversations like we do now. They couldn't share rapid updates, coordinate laws, or maintain cultural unity. They drift apart naturally, becoming independent not by choice but by necessity. Entire generations would live and die between messages. And if you travel near light speed, time itself behaves differently. As Einstein showed, and as countless experiments confirm, the faster you move, the slower time passes for you compared to observers who remain still. This isn't just clocks ticking slower. It's your heartbeat, your aging, your entire experience of time stretching out. From your perspective, everything feels normal. But from the outside, your time moves differently. Space, time, motion. Everything becomes intertwined in ways that feel almost impossible to imagine. Time passes normally for you. It's everyone else's time that seems to move faster. Imagine a spacecraft capable of reaching 99.9% of the speed of light. Not quite light speed, but extremely close. You step aboard this ship and travel to a star 10 light-years away, then turn around and come back. From Earth's point of view, the round trip takes about 20 years, just over 10 years each way. But for you, because of time dilation, the experience is very different. At 99.9% of light speed, time passes about 22 times slower. So while 20 years pass on Earth, you would only age about 11 months. You would return having aged less than a year, while everyone you knew aged 2 decades. Your younger sibling might now be older than you. Your children might now be adults older than you. You would have traveled into their future. If you traveled even faster, say 99.99% of the speed of light, you could journey 100 light years away and back. From Earth's perspective, more than 200 years would pass. But for you, only a few years might go by. You'd experience a short mission, only to return to an Earth centuries older. Everyone you knew would be long gone. Cultures changed, governments transformed, languages evolved. You would return to a completely different world. Now let's zoom out. The observable universe is about 46.5 billion light-years in ray days, roughly 93 billion light-years across. This is the limit of what we can see, not because our telescopes aren't powerful enough, but because light from beyond that horizon simply hasn't had enough time to reach us. Beyond that, space is expanding so quickly that the light will never reach us at all. Within this observable universe are an estimated 2 trillion galaxies, each containing billions or trillions of stars. Multiply it out, and the total number of stars is around 200 billion trillion, a number so large it barely means anything to us. And because most stars are planets, the universe is filled with worlds, more than we could ever count or visit. On the largest scales, the universe forms a cosmic web. Galaxies gather into groups. Those groups form clusters. Clusters form superclusters, and those superclusters stretch across space in massive filaments. Between these filaments are enormous voids, vast, empty regions spanning hundreds of millions of light years. Meanwhile, the universe continues to expand. Nearby objects, the moon, the planets, stars in our galaxy, aren't affected because gravity holds them together. But across hundreds of millions or billions of light years, space itself stretches and carries galaxies farther apart. Some galaxies are receding from us faster than light, not because they are moving through space at that speed, but because the space between us is expanding. Their light will never reach us. We are permanently cut off from them. Given the huge number of stars and planets and the age of the universe, it seems likely that life exists elsewhere. Yet the universe appears silent. No signals, no megastructures, no engineered light, no detectable technology. This is a Fermi-paradox. If life should be common, where is everybody? Part of the answer is distance. Our radio broadcasts have only been traveling for about a century. They've reached about 100 light years in every direction, a tiny bubble in a galaxy 100,000 light years wide. And even within that small bubble, our signals are weak and nearly impossible to detect. Light years change how we think about communication with alien civilizations. If another technological species existed 50 light years away, their signals reaching us today would be 50 years old. If we answered immediately, our reply would arrive 50 years later, a 100-year round trip for a single exchange. You could ask a question and never live to hear the answer. Communication will be more like exchanging history books, not conversations. It's possible the galaxy is full of civilizations, but each so far apart that they never contact each other. Each rises, flourishes, and dies alone, isolated by distance and the speed of light. This idea is lonely, but also beautiful. It means every civilization that does arise is rare and valuable. If we are alone or effectively alone, then we carry a unique responsibility. We are the universe becoming aware of itself, here, in this tiny corner of space. Our thoughts, our art, our discoveries, all of it might be unique within dozens or hundreds of light years. A light year is simply the distance light travels in 1 year, 9.46 trillion kilometers. A unit so huge that we use it instead of kilometers when talking about stars and galaxies. The nearest star, Proxima Centauri, is 4.24 light years away. Our galaxy is about 100,000 light years across, and the observable universe is about 93 billion light years wide. When you look up at the night sky, every star is a message from the past. Sirius is 8.6 years old by the time its light reaches you. Betelgeuse, hundreds of years. Some galaxies we see are as they were more than 13 billion years ago, when the universe was young. Understanding light years puts life into perspective. Our daily problems, our stress, our arguments, all of them happen on one small planet orbiting one ordinary star. But this doesn't make your life meaningless. Your experiences are real and important to you. The universe may be vast and indifferent, but you are conscious within it, capable of understanding it, capable of appreciating its beauty. We are tiny, but we are remarkable. We measure the cosmos, map billions of stars, discover planets around distant suns, and peer back toward the beginning of time. We may never travel to other galaxies. We may never meet other civilizations. But we are here, alive, aware, and capable of wonder. In a universe measured in light years, there is something extraordinary,